Right, welcome back everybody for our next session, which we're going to kick off with Mike Ayers, the President of Global Pavements. Mike's going to be talking about a subject that was mentioned a couple of times, and that's life cycle analysis. Now, this is key, I think, to widening the understanding and appreciation of the whole life benefits of concrete. It's not just cost, it's carbon as well. And Mike's going to talk about what's going on in the States at the moment, which is something we hope to translate into a tool that we can bring to the UK market. Mike.
Thanks, Steve. Good morning. Truly is a pleasure to be here. Haven't been to a meeting in person since March of last year. It's wonderful to be back again. What I'm going to talk to you about today is life cycle cost analysis. And over the course of the last year or so, we put together a program, a tool to calculate life cycle cost as well as carbon footprint. I think you'll find the results of this spreadsheet pretty beneficial for concrete pavements. As you can see by my title slide, I am now this was unlike last time I was here, I'm now the Executive Director for the Illinois chapter of the American Concrete Pavement Association. The last time I was here, I was just with Global Pavement Consultants. But a little bit of background, I worked for the LCCA National from 2001 to 2011. Worked very closely with Federal Highway Administration, worked very closely with state DOTs, and to some extent I still do that. But in this new position, I deal directly with the state government in the state of Illinois. And so I face a lot of the same challenges that you do. My number one mission for my contractor members, my cement suppliers, all those folks, is to build more concrete pavements. So how do we do that? Well, the life cycle cost analysis that we're going to look at has some of the key ingredients to getting that decision based on actual hard data, not just, well, we think concrete lasts longer. So what is life cycle cost analysis? It essentially is an analysis tool. And by itself, it doesn't really carry much weight in terms of being to analyze a pavement structure. So we do an independent design, and we feed that design into a life cycle cost analysis program or spreadsheet such as we're going to look at here. It identifies a strategy that gives you the best value long term, or as we like to say, best bang for the buck. So if I spend $1 today, what's it going to cost me in the long term to maintain that payment? That dollar becomes $1.15, it becomes $1.30. It depends on the design decisions and the type of pavement that I construct. Obviously, the environment, the level of traffic, and many other factors. Illinois is one of the unique states that we actually have a life cycle cost program that does a rudimentary pavement design, and that design then feeds the spreadsheet for LCCA. I'm not a big fan of it. And there are much, much more robust and better design schemes than we use in that spreadsheet. So my preference is to design using the best available technique that you have, take that data, feed it into here. So you already have guidelines to allow you to do that. But there are other things that you might want to consider moving forward, and I'll get into a little bit of that. It's not an engineering tool. This program or this methodology does not tell you when you're going to need to apply a specific type of rehabilitation measure. I'll show you some guidelines that we used in the program, but these are not set in stone. And as you'll see, there's a great diversity of what needs to be done when, depending on the agency that you're dealing with. So generally speaking, these trends are true. So pavement type condition. We have asphalt and concrete, and I apologize for the lightness of the concrete, but So concrete pavements will typically last considerably longer till they reach the end of a design period where they need some type of heavy-duty maintenance or rehabilitation activity. Asphalt will undergo numerous cycles up until that point. And that is the key ingredient in life cycle cost. Because although asphalt pavements are frequently cheaper to construct initially, for a variety of reasons, they cost more to own in the long term. And you see that reflected over here. Concrete starts out at a higher cost initially, but by the time you pass the first or sometimes the second maintenance rehabilitation cycle, concrete becomes the clear winner. The difference becomes more and more profound the heavier volume of traffic that you have. So for us, let's say for an interstate highway, in a rural area, that difference might be 10%, might be 15%, because the volume of traffic is relatively low, and if you consider user cost, it's a big input. If you go into an urban area, Chicago, Dallas, Fort Worth, any of the major cities would have a preponderance of concrete pavements. The reason is because that gap is huge. If you throw user costs in at anything more than about a 5% rate, it predominates the calculations. In this spreadsheet, we don't even consider user costs because it is such a wildly variable number depending on the level of traffic. So the analysis period, what should we actually be looking at? Well, we have initial construction, and we're going to have at least 1, 2, sometimes 3 or 4 maintenance rehab cycles in order to give us a full picture of what the pavement's going to cost. Something else we haven't incorporated in this spreadsheet, but you actually could, is a residual value. So what's an existing asphalt pavement in place worth? What's an existing concrete pavement in place worth? Well, it comes down to how much of that material can you recycle? If you want to look into the carbon footprint of it, how much does it take to recycle concrete pavement, and where can you utilize it? In the States, we're now using up to 100% of recycled concrete in the structure that we're going to rebuild. So the carbon footprint of that is considerably less. We rarely reconstruct pavements. When we do, it's generally 40, 50 years. It's a long, long time. Asphalt pavements we typically reconstruct top to bottom on a more frequent basis. 30 years, 35 years is the typical. So if you look at what the recommendations are, Federal Highway Administration recommends 35 years as a minimum. ACPA, for who I work, 45 to 50 years plus. The reason for that is we now have pavement designs that are designed to first rehabilitation cycle at year 60. So think about design elements for a second. What does it take to go from a 30-year design life to a 60-year design life? In terms of fatigue damage, it probably takes an inch, 5 centimeters of thickness, 2.5 centimeters of thickness. We don't fail pavements by fatigue. We fail pavements because of material degradation. If we can handle that aspect of the pavement, we can make them last a tremendous number of years. But anyway, let's just leave it for the time being and say that it's roughly double the design period should be the analysis period. So this is, there's going to be 5 or 6 slides that are extractions from the spreadsheet, just to give you an idea as to what it looks like. So this is general design inputs. We put our design life in as, we've got 25 years, and you can change that to whatever number that you like. When you change that number, it changes the entire spreadsheet to reflect the design period that you've entered. So remember, we're doing an external design. We're taking those numbers, we're feeding it into the spreadsheet. We're going to analyze this for 50 years, which is twice the design period. We put in 3 different types of pavements in the spreadsheet: CRCP, jointed plain, and then asphalt pavement. You can also, in addition to using the spreadsheet for new pavement construction, you can use it for overlays. So we want to compare the alternatives to an asphalt versus a concrete overlay. You simply don't put in the input values for the pavement support conditions. You put in what you're going to be constructing on top of. So this is just giving you basically length, width, but not depth, because the depth can be done independently for each of these types of pavements. The key ingredient is to make this methodology work with any life cycle cost whole life analysis program is you have to have equivalent designs. But how do you come up with that? And what's it based around? Is an equivalent design is going to be different between asphalt and concrete simply by virtue of the pavements react differently to loads. So concrete pavement that is, let's say 30 centimeters thick, you probably won't fail that by fatigue. If you take a 30 centimeter full depth asphalt pavement, you very could, deteriorate that pavement based on loads through rutting and through shoving and some different types of asphalt related distresses. So what's an equivalent design? It's not 30 centimeters. It's not a direct one-to-one comparison. It ought to be based on load carrying capacity to a specific point of deterioration. But that's kind of getting in the weeds for the talk we're talking about, or the topic we're discussing. If you really want to expedite running the spreadsheet, you simply fill it out for all the design inputs, all the basic parameters, and then come back and just make changes in specified areas. Okay, so I know that I designed this pavement for 25 centimeters. What would happen if I designed it for 30 centimeters? I don't have to change all the rest of the design inputs. I simply change what it is that I'm trying to evaluate. If I wanted to change the percentage of steel in a CRC pavement, I want to change joint spacing and I want to change dowel bar diameter. I can do all those independently and actually use it to evaluate design features as well as the overall life cycle cost. So for example, a jointed plain concrete pavement, and I know that is not the accepted standard, but this is just purely my opinion, is something that you really should seriously consider. They are cheaper. We have an incredible amount of data on jointed plain concrete pavement performance. Noise doesn't have to be the issue. Premature failure doesn't have to be the issue. We know how to resolve those things. We can make a quiet, long-lasting pavement. It may not be zero maintenance the way that we look at CRCP, but it's darn close. And when you build CRCP by virtue of the amount of steel, obviously it's going to cost more. And we'll see that number at the end. But anyway, keep in mind when we get through these, we put in what we think are representative sizes of tie bars, dowel bars for load transfer, joint spacing, thickness of pavement, all the things that you would need to construct this pavement are in this program. So what does a future agency cost? This is the real key element of this. You have to figure out how the pavement's going to fail, when it's going to fail, and how you're going to fix it. That's essentially what that slide is all about. You can do preventive maintenance activities. Rather than allow the pavement to ever get down to the level that you have to do heavy-duty maintenance and rehabilitation, you can come in and intervene. So I have a pavement that has some premature joint deterioration. So I do partial depth repairs or shallow depth repairs only at those locations, and it will greatly improve the longevity of the pavement. So in the program, this is another excerpt. Illinois DOT, Illinois Tollway, which is predominantly CRC pavements. Illinois DOT, predominantly jointed plain concrete pavements. Wisconsin DOT, Indiana, and I have a tremendous number of states that I compared. The numbers that you see there are the ones that are in the program, the ones that are highlighted in yellow as the recommended rehabilitation and maintenance procedure. One thing that I'd like you to keep in mind, that somewhere at around year 25, most states program one of two things. They do a thin, non-structural asphalt overlay to create a smoother riding surface, to improve surface friction, to reduce noise. Rather than do that thin asphalt, and you'll see the effect of it, rather than do that, diamond grinding, according to the new techniques and the new configuration of grinding pattern, will achieve the same result without having to overlay it, without changing grade, without doing all the other things that we really don't want to do on our mainline roadways. So preservation and rehab costs, what is it going to cost me to do this stuff? If you have historical data, then you have solved a lot of the problems. If you don't have historical data, then it becomes an issue of trying to predict what future costs are going to be. So we've already got timing established. We go back to that slide, that's where the timing comes from for each of those individual rehabilitation procedures. So from that, we put in some type of a unit cost for each one of the activities. And what you'd like to use is actual historical data. And if you can't, you can estimate what the materials cost is going to be and the equipment and the labor costs moving forward. Excuse me. When we do a comparison, we're taking future costs, we're bringing it back to current day value. We can do that in one of two ways. Net present value is the simplest form and the one we always use, but there is the uniform annual cost that you could use if you decided to. That's the way you want to envision the pavement. The only benefit of equivalent uniform annual cost is that it allows you to program money in for the future. As so I know at this year 17, I'm going to be doing this activity. This is how much money it's going to cost me to do that. And then finally, you want to compare results. Which of the options that I've input is the best in terms of servicing the public need? If two of them are very close together, you want to take the less risky alternative, obviously. So life cycle cost comparison. We went through and put in designs that are realistic for moderate to heavy traffic. This continuously reinforced pavement, this is 25 centimeters, this is 30 centimeters, this is an equivalent design to the CRCP. And it consists of the surface course and binder courses and the entire structure. So it comes up with a unit cost for materials, it comes up with the placement cost, and those are separated out, and then it totals up the maintenance and rehabilitation cycles as a term net present value. You add all those up together, and that is what that pavement will cost you to own for 50 years. You remember we established 25-year design life, but 50-year analysis. So if you look at these options, this is based solely on the cost to construct and the cost to rehabilitate. We're all roughly 5 million, roughly 4.8 million, 7.2 million. So in this particular case, with the numbers we ran, the asphalt pavement turns out that it is more expensive. Why is that? Is that based on M&R costs? Is it based on initial pavement costs? Since the market fluctuates so much and contract bid prices fluctuate as well, those numbers will change frequently. So your job is to take the numbers, take the spreadsheet, put in the latest and greatest accurate numbers that you happen to have, and crank through these numbers. Jointed plain is roughly 4% higher cost than the JRC, or the jointed plain concrete pavement. In the US, we've run the same analysis. We get CRCP as being about 15% higher. CRCP versus asphalt, we're 69%. For JPC, we're 66%. So obviously, in terms of cost, with the analysis that we performed, concrete is a cheaper alternative. But what we've talked about this morning several presentations, carbon is an ever-increasing part of the decision-making process. So if you go back into the spreadsheet, it ties into all the material quantities that are necessary to build this pavement. And it also looks at what the future costs are. If you're going to do M&R, you're going to do a thin asphalt overlay, you're going to be doing some procedure, what's the value of that in terms of carbon footprint? So these numbers are published numbers. And those numbers are somewhat variable, and if you look in the literature, you can find different values, but those are pretty representative. The ones that have the kind of an orange crosshatch, that is 208 kilograms per cubic meter. That assumes that you're using some type of a supplemental cementitious material besides pure cement. So it might be cement plus fly ash, it might be cement plus slag. Both of those are the default position in the U.S. And it's not necessarily because of carbon footprint, that's just an offshoot. It is not necessarily because of economy. It's because it kills ASR reactivity and because it gives us longer lasting, better concrete at some percentage of addition. But 208 can also mean something else. That could be Portland cement modified with limestone. Portland Cement Association, this is a really big emphasis area for them right now, Portland Limestone Cement or PLC. Lots of research, lots of beneficial things in doing that. The cement companies produce it so that we have full buy-in pretty much. So if you go down through this list and you find that the asphalt overlay is a fairly high number. The asphalt overlay is almost as much carbon-wise as the mainline pavement and the shoulders. So if you want to make a huge impact, don't do that. Diamond grind it. Diamond grind it, full depth repairs, partial depth repairs, joint resealing, whatever it happens to be, is going to be one heck of a lot less than that number. That's one of the options you can do. There are other things, but that is the most obvious thing. So the carbon footprint for jointed plane is higher than it is for CRCP, even though we have a whole bunch of steel in this. Why? Is because 25 centimeters thickness, 300 centimeters thickness. If you make these equivalent, JPC is the cheapest alternative in terms of carbon. But the real comparison, that's asphalt. That is a lot of maintenance and rehabilitation cycles in 50 years. 4 to 6, depending on the number that you want to plug in. That, relative to these numbers, makes a very clear case as to what the most environmentally beneficial option is. And just one last thing, we talked about overlays a little bit, and that there is a gap in current understanding and adoption of overlays, concrete overlays. We have new design methodologies, we have reams of data on projects and whatever. Be glad to share that with you and help in whatever way I can for the adoption of doing concrete overlays on asphalt or concrete on existing concrete. Bonded overlays, unbonded overlays, there's a lot of different options. But if you plug the numbers for that in here, you'll get the same kind of effect. So it is certainly worth looking at. So this is what the program will ultimately do. It allows you to enhance stability to compare pavement types and design features. It updates rehabilitation strategy. All you have to do once you get accumulated data is to change the numbers, the frequencies, and the type of repairs you're going to do. And finally, this stuff is bulletproof. I mean, it is clearly scientific, economically based comparisons. you can change the numbers, you can change the input values, but in the ranges we looked at, the results are always the same. And with that, are we gonna wait for questions? Okay.